Welcome to my Praat series, episode 2. We're going to be learning about how to understand a spectrogram and learn some of the basic features and settings of Praat. Let's get to it. Here is my Prezi number 2, Spectrogram 101, exploring frequency, intensity, and time through spectrograms. Essentially, a spectrogram is a way of visually showing what sound looks like so that we can study aspects such as pitch information or the frequency of vocal vibrations, how loud a sound is or the amplitude of the sound wave, and temporal concepts such as voice onset time and the perception of syllabic stress, etc. Essentially, representing sound visually helps us analyze it with higher accuracy. A spectrogram shows the visual of how an audio signal changes over time. The intensity of the sound shows up as the darker bands on the screen, like here and here. We'll talk a lot more about those formants later. The functional applications of being able to visualize sound include identifying speech sound patterns, visualizing sound frequency distribution, enhance your acoustic analysis skills, understand speech clarity variations, and detect timing and rhythm in speech. In this presentation, I have taken actual screenshots of recordings of my own voice, as well as the step-by-step process I take to analyze my recordings. How do we open the spectrogram view? First, you select your sound object. You either go to Open and select the .wav file that you have saved, or if you've just recorded it, it will appear in your Praat object window. In this example, I decided to analyze the loud hey, which is as loudly as you can without yelling, project hey 2 times. After you've highlighted the piece you want to analyze in the object window, select this View and Edit button. When you get to the editor window, you will see volume information on the top and pitch or frequency information on the bottom. Now I'm going to quickly show you how you can remove some of the visual noise to focus on the aspects of the speech signal that you really want to analyze. Praat has optional overlays which might be automatically turned on. And if that's the case, you'll see lots of distracting lines and dots, etc. The good thing is you can manually disable these additional data with a simple toggle. So when you're in the sound editing window, there will be tabs for pitch, formants, and pulses overlays, and you can toggle them on or off to isolate the specific variable you are focusing on. Now, I pulled these from my undergraduate notes from my Linguistic Cognitive Science course at McMaster University. I was told to set the window length at decimal 005. The dynamic range should be set between 50 decibels to about 100 decibels. And the pitch range you'll want to set is between 75 hertz and 5,000 hertz, which is the maximum frequency for adults. Or if you're analyzing a child's voice, make the top pitch range up to 8,000 hertz. Set the lower pitch range to 50, and with these values, you should be good to go for accurate acoustic analysis. Okay, I'm excited to get into vowel patterns because I find formants to be fascinating. So in a spectrogram, vowels are represented by these dark bands. You can clearly see the first couple of formants. If you check out my resonance video, you'll get a better understanding of what a formant is and its relationship to the fundamental frequency or the basic pitch of a human voice. I found it so interesting to learn that the first formant, or F1, in a sound signal indicates the height of the vowel sound. So as an example, say the sound E as in cheese. E. Can you feel your tongue is high and front in your mouth? E. Now contrast that to say the sound ah as in hot. Ah. E-ah, e-ah. If you alternate between an E and an ah, you will actually feel your tongue moving up and forward for the E and down and back for the ah. I love that example to help build proprioception and interoception into where does your tongue move, where does it occupy space in order to elicit a certain sound. So while the first formant teaches you about the height of the vowel. The second formant, or the second dark band, tells you information about the frontness. Is it near the front of your mouth, like a E sound, or is it toward the back of the mouth, like an ooh or an ah? Although that's pretty cool, vowels are not the only speech sounds we have. We also have a class of sounds called fricatives, which are kind of the whistlier ones, the ones that are kind of more difficult to parse over a poor connection telephone call. Those S, F, sh. So fricatives are characterized by turbulent airflow and high frequency energy. This results in noisy sound patterns, and you can actually see that the higher pitches in this sample are darker, meaning more intense. So it's really interesting that perceptually what we hear, shh, it sounds like a higher, squealing, pitchy, noisy kind of sound, and that is visually represented on the spectrogram, which is nice because it makes reading spectrograms a little bit more intuitive. Almost like the Booba Kiki linguistic experiment where there was a roundish shape and a more jagged shape, and participants were asked to label each one either Booba or Kiki, and consistently people named the more roundish shape Booba, and they named the more jagged one Kiki, because acoustically there is a connection between what we hear and perceive and what we see and perceive. So when our visual signal aligns with what we expect from the audio signal, that just adds a level of congruence, and it makes it that much easier to process what we're analyzing. The next class of sound that we're going to talk about is a stop. So if fricatives are sounds that we can hold on to, s, f, sh, a stop, as implied by the name, are sounds that cannot be prolonged. P, b, d, k, g. All of those are stops. They completely stop the flow of air, and then once the obstruction is removed, a burst of air follows. So the time it takes from the closure to the onset of the voice, like in the word pot, that's called voice onset time. There's a brief moment for a voiceless stop, p, 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 where your voice is not on and then it has to turn on to get to the vowel, pot. And so the cool thing about a spectrogram is that you're actually able to zoom in close enough to measure the voice onset time for different stops. Now we'll briefly discuss how to select and measure the waveforms. The nice thing about Praat is that it's pretty intuitive, so if you have any comfort with computer programs at all, you probably won't have too hard of a time figuring out how to use Praat. So in this case, you click and drag to select the part of the signal that you want to analyze and highlight it. Now, importantly, if you want to then view the selected duration, you have to make sure that it is less than a 10-second window. If you select something greater than 10 seconds, it's not going to allow you to perform the detailed acoustic analysis that you want to. So this black number here is where it shows you the duration of the sample that you have chosen. So in this case, it would fit within that 10-second window. And the red numbers on either side show you the timestamps of the speech signal within the entire sample. So going into a little bit more detail about the zoom tools. After you've selected the region that you want to analyze, see here I've highlighted the select button. So first I chose that 8.321 section and then click select, and it's going to zoom you in to that visible part. And now see how much detail you can start to see in the signal. If you want to zoom in even further, you hit the in, and if you want to zoom out, you hit the out. Pretty straightforward. Being precise about the frequency range you choose to include in your measurements can help you really hone in on the class of sound that you're wanting to study in detail. So if you know that you are interested in fricatives, then you can cut off the lower frequencies, which give you mostly acoustic information about vowels. And conversely, if you're mostly interested in the vowels, you can choose to narrow your range of study within that lower frequency field. Here's some general troubleshooting tips. If your spectrogram is not looking right, you can increase the dynamic range to make sure that you are getting more data to consider in the sample. You can shorten the window length, meaning you're getting rid of excessive information that's distracting. You can raise the maximum frequency, and you can turn off overlays if your waveform is looking too cluttered. And you can turn off overlays if your spectrogram is looking too cluttered. What are your key takeaways from this video? Spectrograms represent sound visually. The settings that you input before conducting your analysis impacts the clarity and accuracy of your analysis. There are well documented visual patterns for different classes of speech sounds, such as vowels versus fricatives versus stops versus affricates versus nasals. And Praat can help you prioritize clean viewing by untoggling extraneous functions you don't need to consider at the moment. So I think my strategy is probably going to be pump out the academic content first, and then once those basics are down, because I'm having a lot of feedback, apparently acoustic science isn't the most fascinating subject. So I'm happy to help take a little bit of the learning burden off. It's pretty cool knowing the information, but learning it and encoding it can be a drag. So let's get through the dry stuff, and then we can do some fun acoustic analysis. I have a couple interesting toys I plan on bringing from the clinic to do a couple playful demonstrations with different acoustic signals. So stay tuned for the fun stuff. And in the meantime, thank you for tuning in. I'm really glad you're here. Keep your chin up, and we'll nerd out together again soon. Hang in there. And again, thanks for stopping by.